Hello dear students, welcome to a whole new session. In this session, we will be learning the chapter Circles. Before moving to the main topic, let's recollect what a circle is. What is a circle? In two possible definitions, a circle can be defined as a collection of points that are equally spaced from a middle point. I'll repeat. A circle can be defined as a collection or set of points that are placed equally from a middle point. I hope that's clear. Now, in a second method, we can define a circle as the path traced by a single point rotating around a middle point, provided the distance between the points remain constant. That's right. Let's have a look at the terminologies related to circles. Now you can see in this figure, a circle will definitely have a center. So in this figure, C is the center of the circle. Now there is a line drawn connecting the center of the circle to a random point on the circle named P. We can call that the radius. Also, PC is a radius, then QC is a radius, RC is radius. So, infinitely many radii can be drawn in a circle. Now, the next line that we can see is QR. What is QR? That is a line that connects two points, Q and R, and one more condition, the line is passing through the center of the circle. That is called the diameter of the circle. So what is a diameter? The line that connects two oppositely placed points and the center of the circle. That is a diameter. Now there is a relation between diameter of a circle and its radius. Diameter will always be 2 times the radius. If we denote diameter using the letter D and radius using the letter R, we can say that D is equal to 2R as given. Now the next one is a line PR that is simply connecting 2 points P and R. Now we can see this line doesn't have any important point passing through it, or this line is not crossing through any other point within the circle, right? Such a random line is called a chord. You can see the line LN, and that is touching the circle at one point M. Now that line is called the tangent to the circle. What do you mean by a tangent? A tangent is a line that touches a circle at only one point. You can see that the tangent LN is passing only through the point M, or the tangent is coming in contact with the circle only at M. So LN is the tangent and M can be called as the point of contact. Now let's discuss some properties that tangent of a circle exhibit. To begin with, tangent only touches a circle at one point. I'll repeat, a tangent touches a circle at only one point. Look at the tangent AB, and the point of contact of the tangent is C, which means that the tangent AB will have only one point of contact, that is C. Now the second property, a circle can have any number of tangents. You can see there is a tangent AB touching at C, there is a tangent PQ touching the circle at R, and there is a tangent TU touching the circle at V, and you can draw around infinitely many tangents for a single circle. The third property is somewhat like the converse of the first property. So the third property states that a point on a circle will only have one tangent, which means that let's take the case of the point of contact R in the figure. You can see that through R only PQ can pass. Well, we can draw many lines as shown in the figure through R, but all the other lines won't be tangents. Only PQ will be the only tangent that is passing through R. Now the fourth and final property of tangents is that tangents will never penetrate a circle, which means that tangents will never get into the circle. You can see the red line above the tangent TU it is totally penetrating the circle, and that is not possible. If it does, then it is not called a tangent. Now let's get into the main concepts. In this chapter, we will be learning two theorems related to tangents of a circle and their proofs. So let's start with Theorem 1. Theorem 1 states that the tangent at any point of a circle is perpendicular to the radius through the point of contact. I can explain that with the given illustration. We can see a circle with center O and a radius OE. We can see that through E, as in with E as the point of contact, a tangent DF is passing. As per Theorem 1, the tangent at the point E, that is tangent DE, is perpendicular to the radius OE through point of contact, that is E. So the angle that E makes with respect to the tangent and the radius is 90 degrees. The proof of Theorem 1. Before doing the proof, we have to bring about some constructions in the illustration. Pick any two random points P and Q on the tangent and connect them both to the center O. So join OP and OQ where P and Q are randomly picked points. Now also mark the points where OP touches the circle as A and the point where OQ touches a circle as B. Now you can notice that OA, OE and OB are all radii of the same circle. So we can mark those as small letter r or radius. So OA is equal to r, so is OE and so is OB. Now let's begin with the proof. Let's take the line OP. Now OP can be expressed as a combination of OA and AP. So OP is equal to OA plus PA. Now we know that OA is a radius or r, so replace AO with r. So OP is equal to r plus PA. Now we also have to replace r with OE because we know OA is equal to OE is equal to OB is equal to r. So now the equation has become OP is equal to OE plus AP, which clearly means that OP is longer than OE, right? That's right. Now, for any other point, say, even if we take the same case for OQ, we can prove that OE is also shorter than OQ. So, we can conclude that for any points other than E on the tangent DF, OE will be the shortest. Now, let's imagine ourselves crossing a road. Now, we have plenty of ways to get to the other side of the road, as in we can take this path or the straight path. Which is the shortest path that we will take? The straight path, which means that we have to take the path that is perpendicular to the road. We are using the same concept to prove here. So, using the statement, out of all the line segments drawn from a point to several other points on a line, the shortest line will be the perpendicular to the line. So we can say that OE is the shortest, which means that OE is perpendicular to DF, or angle E is equal to 90 degrees, hence proved. Now moving on to Theorem 2, it states that the lengths of tangents drawn from an external point to a circle are equal. Look at the illustration here. You can see there is an external point L and two tangents LM and LN are drawn to the circle. So, according to Theorem 2, LM is equal to LN. We'll move to the proof of Theorem 2. For this one, the construction that we have to make is by joining M and N to the center O and join LO. Now, you can see two triangles, namely triangle LNO and triangle LMO. We can see that angle N and angle M are 90 degrees each. Remember Theorem 1? Radii is perpendicular to the tangent. That's right. Now we can see that LO is a common side. Thirdly, ON and OM are both radii of the same circle. So applying Rhs Congruence Criterion, we can say that triangle LNO is congruent to triangle LMO. By CPCT or corresponding parts of congruent triangles condition, we can conclude that LN from triangle LNO and LM from triangle LMO are equal in length. What are LN and LM? The tangents. So hence proved that the tangents drawn from an external point to a circle are equal in length. Now that we are done with learning the concepts, it's time for us to apply the concepts into the numericals. So let's begin. Let's start with very short answer type questions carrying 1 mark each. The first question. A tangent PQ at a point P of a circle of radius 5 cm meets a line through the center O at a point Q such that OQ is equal to 12 cm. Find the length of PQ. Now in the question, there is no figure given, so we have to sort out the figure. You can see there is a circle and there is a tangent PQ, and they had specified that of a point P of a circle, which means that P is the point of contact. So P is the point touching and Q is the external point. Now let's continue. Of radius 5 cm, the center is O. So you may connect P to the center O and mark it 5 cm. At a point Q, so we already know Q, such that OQ, so now join OQ, that is 12 cm. So we got a complete figure. Find the length of PQ, that's what we have to do. Now we can see that angle P will be 90 degree, applying Theorem 1. That is, tangent will be perpendicular to the radius. So angle P is equal to 90 degree. That makes triangle POQ a right triangle. Now we can apply Pythagoras Theorem in it. QO square is equal to QP square plus PO square. Now 12 square is equal to PQ square plus 5 square. Upon cancellation and transposing, we will get PQ square is equal to 119. 119 is a prime number and it's not a perfect square. So we are left with PQ is equal to square root of 119 centimeter. That is the length of PQ. Now the second question. In this one, the figure is given. So let's read the question. A chord of a circle of radius 10 centimeter subtends a right angle at its center. Calculate length of the chord in centimeters. We can see the figure. There is a triangle AOB with O as the center of the circle, and they had clearly given that radius is 10 centimeter. So OA and OB are 10 centimeter each. That makes it an isosceles triangle. Again, they have specified that the chord will subtend right angle at the center. So angle O will be 90 degree. And that makes it an isosceles right triangle. So we can apply Pythagoras again. So AB square will be equal to OA square plus OB square. We know that both OA and OB are 10 centimeter each. So that makes it 10 square plus 10 square, or 100 plus 100. Now the final answer will be AB is equal to 10 root 2 centimeter. Let's move on to the third question. In the figure, so the figure is given, TP and TQ are two tangents at a circle with center O, such that angle POQ is equal to 110 degree. What is the measure of angle PTQ? So they have clearly given the figure. We can see that angle POQ is equal to 110, that has been given. Now applying Theorem 1, we can say that angle P and angle Q are 90 degree each. So we can also observe that POQT is a quadrilateral. Quadrilateral polygon having 4 sides. Now what is the angle sum of a quadrilateral? 360 degree. So we can write angle P plus angle O plus angle Q plus angle T is equal to 360 degree. Putting the values for P and Q as 90 degree and O as 110 degree, we can solve and we will get angle T or angle PTQ as 70 degree. Moving on to the next question. Prove that the tangents drawn at the ends of a diameter of a circle are parallel. This is a prove that type of question. So we have to draw the figure by ourselves. So let's begin drawing a circle, and the question is to prove that the tangents drawn at the ends of a diameter. So we have to draw a diameter first. So in this figure, ZU is the diameter. You can see that passing through the center O. Now at the ends of diameter, 2 tangents had been drawn, namely XY and ST. Now at angles Z and U, we have to make 4 divisions, namely angle 1, angle 2 at Z and angle 3 and angle 4 at U. Now we can see that angle 1 and angle 4 are alternate interior angles. So are angle 2 and angle 3. Now using theorem 1, we can say that all these angles, angle 1, 2, 3 and 4 are 90 degree each. Why? Because OU is the radius and ST is the tangent. So OU is perpendicular to ST. Now OZ is perpendicular to the tangent XY. So 1, 2, 3 and 4 are 90 degree each. Therefore angle 1 and angle 4 are equal and they are alternate interior angles. When are alternate interior angles equal? When the lines are parallel. So we can conclude that XY is parallel to ST. Moving on to question number 5. In the given figure, PA and PB are 2 tangents drawn from an external point P to a circle with center C and radius 4 cm. If PA perpendicular to PB, then find the length of each tangent. So we can see the figure on the extreme right side. And you have to bring out a construction by joining AC and BC. Now we can say that angle A and angle B are 90 degree each by applying theorem 1. That makes APBC a square. If you have doubt, you can check that with angle sum property of a quadrilateral and properties of a square. So APBC is a square, and in the question it's given that the radius is 4 cm. So in a square, all the sides are equal. So all the sides will be 4 cm. Hence, we can prove that the tangents will also measure 4 cm each. We shall begin with short answer type questions carrying 2 marks each. In the given figure, sides AB, BC and CA of a triangle ABC touch a circle at P, Q and R respectively. If PA is equal to 4 cm, PB is equal to 3 cm and AC is equal to 11 cm, find the length of BC in centimeter. So some measurements had been given. So draw the figure in your book and take down those measurements close to the figure. So AP equal to AR, both are 4 cm each by applying theorem 2. Now we can find the length of RC because the total length of AC is 11 cm. So RC will be 11 minus 4, that is equal to 7 cm. Now RC is equal to QC. So both RC and QC will be 7 cm each. Again theorem 2. Now BQ can be equated to BP, that is equal to 3 cm. Also BQ and BP are tangents from the same point B. So BQ is now 3 cm. So the total length of BC can be written as BQ plus QC, that is equal to 3 plus 7, 10 cm. Now let's move on to the next question. In the given figure, a circle is inscribed in a quadrilateral ABCD, touching its sides AB, BC, CD and AD at P, Q and R respectively. If the radius of the circle is 10 centimeter, BC is equal to 38 centimeter, PB is equal to 27 centimeter and AD perpendicular to CD, then calculate the length of CD. So many datas are given, so you may list down the given datas first and you may construct OR. Connect O, the center O, to the point of contact R of the tangent DC. Now you can see that angle S and angle O are 90 degree because tangent is always perpendicular to the radius at the point of contact, Theorem 1. Now angle D is equal to 90 degree, which makes ORDS a square. So in a square all sides are equal, so we can say DR is equal to 10 centimeter. Now moving on to the next part, BP is equal to BQ is equal to 27 centimeter, Theorem 2. Tangents from an external point are equal in length. So CQ can be found by subtracting 27 from 38. So 38 minus 27 will give you 11 centimeter. So BC and CQ are 11 centimeter, Theorem 2. So DC can be written as DR plus RT, that is 10 plus 11, 21 centimeter. Moving on to the next question. In the figure, AB is the diameter of a circle with center O and AT is a tangent. If angle AOQ is equal to 58 centimeter, find angle ATQ. This is a frequently asked question. Before moving on to solving this question, have a look at the figure in the extreme right side. You can see a circle with center O and there are 2 points P and R anywhere on the circle. Now P and R are both making 2 sets of angles or 2 angles, namely angle POR at the center of the circle and angle PQR at some other point on the circle. Now there is a theorem that connects these 2 angles O and Q. According to the theorem, it states that angle Q or angle PQR will be half of angle subtended at the center. That is, angle PQR will be 1/2 into angle POR. Now that is the idea that we will be applying in solving this question. You may notice in our figure that angle AOQ is equal to twice of angle ABQ. So we can say that angle ABQ is equal to half angle AOQ. That is equal to half into 58 is equal to 29 degree. So angle ABQ is equal to 29 degree. Now angle BAT is equal to 90 degree applying Theorem 1. Even though OA perpendicular to AT, BA is the diameter, so we can write angle BAT is equal to 90 degree. Now in triangle ABT, we can apply angle sum property. So the angle sum in a triangle is 180 degree. Upon solving, we will get the measure of angle T as 61 degree. Moving on to the next question. 2 concentric circles are of radii 7 centimeter and r centimeter respectively, where r is greater than 7. A chord of the larger circle of length 48 centimeter touches the smaller circle. Find the value of r. I'll repeat the question again. 2 concentric circles are of radii 7 centimeter and r centimeter respectively, where r is greater than 7. A chord of the larger circle of length 48 centimeter touches the smaller circle. Find the length of r. So there are 2 concentric circles and they had clearly given that r, the radius r is greater than the radius 7. So the radius r is the bigger circle and 7 comes inside. Now we have to draw a chord AB of 48 centimeter. Now in the triangle OAC, we can see that angle OCA is equal to 90 degree, tangent is perpendicular to the radius, or theorem 1. Now we can apply Pythagoras theorem in this triangle. So we can write OA square is equal to OC square plus AC square. Now AC is half of this chord AB. So AB is 48, so AC will be 24 centimeter. So Pythagoras theorem will give you R square is equal to 7 square plus 24 square. Upon calculating, we will get the value of R as 25 centimeter. So the radius of the bigger circle is 25 centimeter. Next question. In the figure, a quadrilateral ABCD is drawn to circumscribe a circle with center O in such a way that the sides AB, BC, CD and DA touch the circle at points P, Q, R and S respectively. Prove that AB plus CD is equal to BC plus DA. This is yet another important question, a very frequently asked question. So here the figure has been given. There is a quadrilateral ABCD touching a circle at, enclosing a circle touching at the points P, Q, R and S. So we have to apply theorem 2 in all possible tangents. So we will get 4 pairs of equal tangents. We have to list them out. So let's do that. By theorem 2, AP is equal to AQ, BQ is equal to BR, CR is equal to CS and DS is equal to DP. Now we have to prove that AB plus CD is equal to AD plus BC. So let's begin from LHS, write AB plus CD. Now we know that AB has been constituted with 2 parts, namely AQ and BQ. Similarly, CD can also be written as CS plus DS. Now AQ, BQ, CS and DS can be replaced with their equal values. So the equation becomes AP plus BR plus CR plus DP. Now AP and DP can be written together and BR and CR can be written together. AP plus DP will give you AD and BR plus CR will give you BC, hence proved. Now let's move on to the third type of question, long answer type questions carrying 3 marks each. This is yet another frequently asked and very important problem. So the question is, prove that the parallelogram circumscribing a circle is a rhombus. So we are not given the figure, we have to sort out the figure. So let ABCD be a parallelogram and let a circle be inside ABCD and let the points of contact be P, Q, R and S. So since ABCD is a parallelogram, all the sides opposite sides will be equal. So we have to prove that parallelogram ABCD is a rhombus. So what is a rhombus? All sides will be equal. So from opposite sides be equal, we have to arrive at the conclusion that all the sides are equal in ABCD. So again, applying theorem 2, we have to list out all the equal components or write down all the equal pairs of the tangents. So that goes like this: AP is equal to AQ, BQ is equal to BR, CR equal to CS and DS is equal to DP. Again, starting from AB plus CD or sum of opposite sides, we can replace AB and CD with their constituent parts. So AB can be written as AQ plus BQ and CD can be written as CS plus DS. Now those can be replaced with their equal values, and upon rearranging we can prove that AB plus CD is equal to AD plus BC. Now because ABCD is a tangent, instead of writing AB plus CD, we can write AB plus AB. Why? Opposite sides are equal, so AB will be equal to CD. So instead of writing AB plus CD, we can write AB plus AB. Similarly, on the other side, we can write AD plus AD. So the equation becomes 2AB is equal to 2AD, or we can cancel the 2 common on both sides, so we can cancel them. That becomes AB is equal to AD. Now AB and AD are similar sides, so AB equal to AD. Similarly, all the adjacent sides can be proved to be equal to each other, which means that all the sides of the parallelogram ABCD are equal, so ABCD is a rhombus, hence proved. Now let's go to the next question. In the given figure, an isosceles triangle ABC with AB equal to AC circumscribes a circle. Prove that the point of contact D bisects the base BC. So first let's list out the given data. AB equal to AC. Now we have to prove that D bisects BC. That means BD equal to CD. Again, applying theorem 1, we may list all the pairs of equal tangents. So AF equal to AE, BF equal to BD and CD equal to CE. Now we may add all the three equations. So AF plus BF plus CD will come in the left hand side and AE plus BD plus CE will come in the right hand side. We can see that AF plus BF is equal to AB. So AB plus CD will become the LHS and AE plus CE is equal to AE. So the RHS will become AC plus BD. But we know that AB equal to AC because it's an isosceles triangle. So we can cancel the common terms on either sides. So we have CD equal to BD, hence proved. Next question. In the given figure, a circle inscribed in triangle ABC touches its sides AB, BC and AC at points D, E and F respectively. If AB equal to 12 cm, BC is equal to 8 cm and AC is equal to 10 cm, find the lengths of AD, BE and CF. So again, applying theorem 1, list out the pairs of equal tangents. So AD equal to AF will be the first, BD equal to BE will be the second, CE equal to CF will be the third. From the figure, we can write AD plus BD is equal to 12 cm. Let that be equation 1. Similarly, we can list out equations 2 and 3 as BE plus CE equal to 8 and AF plus CF is equal to 10. So we got 3 equations 1, 2 and 3. Replacing AD with AF in equation 1, the equation 1 will become AF plus BD equal to 12. Let that be equation number 4. Now equation number 4 minus equation number 3, we will get BD minus CF is equal to 2. Mark that as equation number 5. Again, replacing BE with BD and CE with CF in equation number 2, we will get BD plus CF is equal to 8. Let that be equation number 6. Now equation number 5 added with equation number 6, we will get 2BD is equal to 10 or BD is equal to 5 cm. So we can write BE is equal to BD is equal to 5 cm. Now solving equation 6 with the known value of BD, we will get CF is equal to CE is equal to 3 cm. Similarly, from equation 4, we can get the value of AD or AF, that is 7 cm. Here comes the next question. In the figure, AP and BP are tangents to a circle with center O such that AP is equal to 5 cm and angle APB is equal to 60 degree. Find the length of chord AB. So we had given that AP is equal to 5 cm. Applying theorem 2, we can say that AP and BP are of equal length. So AP is equal to BP is equal to 5 cm. With that, we can say that angles opposite to equal sides are equal, which means that angle PAB is equal to angle PBA. Now in the triangle PAB, we can apply angle sum property because we have angle APB as 60 degree and angle PAB is equal to angle PBA. So upon applying angle sum property and simplifying, we will get as angle PAB is equal to angle PBA is equal to 60 degree. So all the three angles of a triangle are 60 degree, which means that the triangle is an equilateral triangle. So in an equilateral triangle, all the sides are again equal. So we can say that AB is also 5 centimeter. So the length of chord is equal to 5 centimeter. Let's move on to the next type of questions, very long answer type questions carrying 4 or 5 marks depending on the curriculum. So the first question in that type, in the figure, xy and x dash y dash are two parallel tangents to a circle with center O touching the circle at P and Q respectively. Another tangent at C intersects the line xy at A and x dash y dash at B. Prove that angle AOB equal to 90 degree. So it is a very important and very frequently asked question. So we have to bring a construction in this by joining O and C, and now we get 4 sections for the whole angle O. So mark all the 4 sections of angle O as L, M, N and R. Now let's begin. So we have to prove that angle M plus angle N is equal to 180 degree. Now let's take triangle POA and triangle COA. In those two triangles, angle P and angle C are 90 degree each because they are the angles made by the radius to the tangent. So they are 90 degree by theorem 1. Now OA is a common side, so there is a common side, and OP and OC are equal because they are the radii. So using Rhs criterion, we can say that triangle POA and triangle COA are congruent. Now by CPCT, corresponding parts of congruent triangles, we can say that angle L is equal to angle M. Similarly, for the other two triangles, we can prove that angle N is equal to angle R. Let's pause a while there. Now we can see that angle L, angle M, angle N and angle R are all lying on a line and are adjacent to each other. So such angles are supplementary, which means that their sum will be 180 degree. So adjacent angles lying on the same line are supplementary. So we can put that into mathematical terms. That will go like this: angle L plus angle M plus angle N plus angle R is equal to 180 degree. Now we can replace the other two angles with M and N. So we'll get M plus N is equal to 180 by 2 is equal to 90 degree. Hence proved. Next question. In the figure, the sides AB, BC and CA of a triangle ABC touch a circle with center O and radius R at P, Q and R respectively. Prove that. You have two parts for this question. First part, AB plus CQ is equal to AC plus BQ. Second part, area of triangle ABC is equal to half into perimeter of triangle ABC into R, that is radius of the triangle. So let's move to the first part. To begin with, list all the equal pairs of equal tangents using theorem 2. So that goes like this: AP is equal to AR, that's the first pair. The second pair will be BP equal to BQ. Then now the third pair will be CQ is equal to CR. Again, adding all on both the sides, on LHS we will get AP plus BP plus CQ is equal to AR plus BQ plus CR. When we combine AP and BP, we will get AB, and combining AR plus CR, we will get AC. So what's remaining? AB plus BQ is equal to, AB plus CQ is equal to AC plus BQ. Hence prove the first part. Moving on to the second part, we have to join all the points to the center, as in join OP, OR, OQ, OA, OB and OC. Now, area of the whole triangle ABC can be written as the sum of areas of three constituent triangles, namely triangle AOB, triangle BOC and triangle AOC. Now, for all the three triangles, they are of the form half into B into H. So, area of triangle ABC is equal to half into OP into AB plus half into OQ into BC plus half into OR into AC. Now, OP, OQ and OR are all radius of the same circle. So, you can replace those three terms with R. Now, R and half are common in all those. Take those out. What's remaining? Half into R into bracket AB plus BC plus AC. What is AB plus BC plus AC? Perimeter of triangle ABC. So, area of triangle ABC is hence equal to half into R into perimeter of the triangle ABC, hence proved. Moving on to the next question. Prove that the angle between the two tangents drawn from an external point to a circle are supplementary to the angles subtended by the line segment joining the points of contact at the center. So, that is a total prove that question. So, we have to do the construction. So, there is a circle, there are two tangents, equal tangents from one external point, and we have to prove that that angle is supplementary to the angle subtended by the radii in the center. So, we have to use theorem 1 and say angle B and angle A are 90 degree each. So, there is a quadrilateral PAOB. So, we can apply angle sum property of a quadrilateral, that is 360 degree. Upon cancellation and substitution, we will get angle P plus angle O is equal to 180 degree, hence proved. Next question. A triangle ABC is drawn to circumscribe a circle of radius 4 cm such that the line segments BD and DC into which BC is divided by the point D, by the point of contact D, are of lengths 8 cm and 6 cm respectively as shown in the figure. Find the sides AB and AC. Now, this is a little tricky question, but it's simple once we get the idea. So, we will write all the given data. BD is equal to BC is equal to 8 cm by applying theorem 2 as well. Similarly, CD is equal to CF is equal to 6 cm. Let the two unknown values AE and AF be x cm. Now the triangle ABC has been divided into three constituent triangles upon joining all the points of contacts and all the vertices to O. So, triangle ABC's area can be written as area of triangle COB plus area of triangle BOA plus area of triangle AOC. Now, we will take RHS one time. So, RHS is the sum of three triangles. So, we can write those as half into base into height. Now, half into OD into CB plus half into OE into BA plus half into OF into AC. Now, OD, OE and OF are all the radii of the same circle. So, you may replace those with 4 cm because in the question it's been given that radius of the circle is 4 and CB, as we can see in the figure, CB is equal to 14. Now, the other one AB is equal to 8 plus x and AC is equal to 16 plus x. So, the equations will be half into 4 into 14 plus half into 4 into h plus x plus half into 4 into 6 plus x. Now, upon cancellation, we can simplify the entire equation and make it into the simplest form possible. So, the RHS will become equal to 4 into 14 plus x. Let's pause a while there. Let's move to LHS, left hand side, that is area of triangle ABC. For that, we might have to look back in the 9th grade portion, Heron's formula. Area of a triangle can be written as root of S into S minus A into S minus B into S minus C, where A, B, C are the three sides of the triangle and S is the semi-perimeter. So we are going to use the same equation to find area of triangle ABC, that is the LHS. So we will first find this S or semi-perimeter, that is equal to 14 plus h plus x plus 6 plus x whole divided by 2, and we will get S is equal to 14 plus x. Now we may list down those. S is equal to 14 plus x, A is equal to 14, B is equal to 8 plus x, and C is equal to 6 plus x. Now we may put it all in the Heron's formula equation. So area of triangle ABC is equal to square root of 14 plus x into 14 plus x minus 8 plus x into 14 plus x minus 6 plus x. So upon cancellation, we can reduce that equation into root of 14 plus x into 6 into 8. Let's pause there. Now we may equate LHS and RHS. So LHS was 4 into 14 plus x and RHS was root of 14 plus x into 6 into 8. We may square on both sides to eliminate the square root. So we will get 4 square into 14 plus x the whole square is equal to 14 plus x into 6 into 8. Now this is a little bit tricky. We will have the tendency to open the brackets and make it more complex. Rather than opening the bracket, keep them as it is. Do not multiply or apply identity. Now you can see that 14 plus x is common on both sides. 4 is common on both sides. Similarly, we can cancel if any common terms from either sides, and what will be remaining is 56 plus 4x is equal to 12x. Or 56 is equal to 8x. That way we can find the value of x as 56 by 8, that is equal to 7. So we can now substitute the value of x to find AB and AC. So we will get the length of AB as 8 plus 7 is equal to 15 centimeter and AC as 7 plus 6 is equal to 13 centimeter. Moving on to the next question. Prove that opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. So there is a quadrilateral ABCD circumscribing a circle with center O, and let the points of contacts be P, Q, R and S. Now for simplicity, we can divide all the sections of O or name all the sections of angle O as A, B, C, D, E, F, G and H. I hope that's clear. Now we may take two triangles. In triangle OAP and triangle OAS, we have AP equal to AS, they have tangents from the same point A, then OP equal to OS, radii of the same circle, and OA is equal to OA as a common side. So by Rhs Congruence Criterion, we can prove that angle OAP and angle OAS are congruent. So by CPCT rule, we can say that angle A is equal to angle B. Similarly, for other triangles as well, we can prove that angle H is equal to angle G, angle D is equal to angle C, and angle E is equal to angle F. Now, you might recollect that angles A to angles H are all lying around the point O, which means that their angle sum is equal to 360 degree. So we can write, adding all the angles, the equation becomes angle A plus angle B plus C plus D plus E plus F plus G plus H is equal to 360 degree. Replacing the necessary angles or the unwanted angles, we can write angle A plus angle H plus angle D plus angle E is equal to 180 degree, or angle AOB plus angle COD is equal to 180 degree. which means that angle subtended by AB at the center is supplementary to the angle subtended by CD at the center. That's what we had to prove. Similarly, we can prove that angle BOC plus angle DOA is also 180 degree. Thank you.